the Optimi. The Optimi sensor system. We're going to talk about the design options and objectives that guided the choices that were made for the Optimi sensors. The heart sensor, the activity sensor, and the brain sensors, and use cases. How to connect and to drive the home PC, which was the software that was used by the subjects in the study. RF protocol and energy savings considerations, and user issues and results, and conclusions and future work. So the Optimi sensor system, as you saw shortly before the introduction, is made of activity sensor, heart sensor, and cortisol sensor that are worn 24 hours a day, all time. The activity sensor is measuring and recording physical activity and sleep quality. The heart sensor, the heart rate variability, sleep quality, HR biofeedback, and cortisol, subthermal cortisol samples. Once per day, the participant records his brain signal through a session with the EEG sensor that is put on the frontal lobe here. To measure alpha asymmetry, C0 complexity, and neurofeedback. The voice, the speech is recorded once a day to measure negative effect and depression. And there's a self-report that is in the form of a questionnaire. And the home PC and the Optimi server. So it's a whole system where it's all wireless. Data is transferred to the PC, and there's a display, and there's a part that is a self-diary report, and everything is then sent to the server. The main objectives and challenges that guided the choices made for the sensors is we had to overcome the inconvenience of cable using wireless, so same like Javier, to maintain the data privacy over the air, designing wearable sensors to be as small as possible and achieve a fit and forget paradigm of these. Sensors must last at least 27 hours between charge, so this was battery and energy saving consideration. And we wanted to remove the need for a personal data assistant by making the sensors compute key physiological data. So to be able to compute as much as possible on the sensor while keeping saving energy at the same time. The electronic design challenge, it had to be small size and lightweight. So the battery size had to be as small as possible, and ultra-low energy consumption, so to use the latest system-on-chip technologies that are available. And there was a high computational demand, so it meant that it required efficient programming to make something very simple but very effective. And high data rate wireless communication, so the solution of the 2.4 gigahertz was chosen. At the start of Optimi, which is some time ago already, there were 4 available options for wireless. Wi-Fi, Bluetooth version 3, Zigbee, and Nordic semiconductor. The 3 first were defined as too energy consuming. So it was for fullest flexibility, we chose to develop a proprietary design around the Nordic semiconductor solution, which is a chip manufacturer, and it was to make it a simple private protocol, and it was giving us the possibility to have data privacy and low power, so really to make a customized thing. And it matched the sensor and user needs, so the specificity of a proprietary solution may offer simplicity and energy efficiency. This was the best solution. This is the ECG sensor, so you saw it from close, so it's more as a necklace. It takes 90 readings, each over 128 beats during a 24-hour period. It takes the average heart rate and the heart rate variability, and it also takes readings of physical motion, so you can compare the data if the person is lying down or if the person is moving. And it has also, there's also a heart rate biofeedback mode that streams HR data in real time for biofeedback for relaxation. And this is the EEG sensor. The picture shows a previous version of the prototype. So it's to put on frontal lobe on the FP1, FP0, and FP2 with the grounds. So it measures the difference in potential. It records up to 30 minutes of raw EEG data on 5 electrodes. 24 bits resolution, 260 hertz, and that was for downloading the information on the home PC. And also, there was a neurofeedback training application that was developed for relaxation, and this is in real time. So the EEG sensor performs a 512 point floating point FFT that is calculated in the sensor, and it streams brainwave frequency domain power levels, so the different bandwidths of beta, alpha, theta, and also the 50 hertz, which is the electrical interference in the environment. So we're able to see if we have too much interference, if the signal is good or bad. So this was used in real time for neurofeedback training. The activity sensor, it was mentioned in the video in the introduction that it was decided to put it on the leg rather than the arm to measure the activity. Like, so if we're moving at the table but we're sitting, actually our legs are static. It records 3-axis acceleration at 0.5 seconds, so a half a second intervals continuously for 36 hours. And the way it calculates the data, the accelerations are using a statistical cloud size of acceleration point, which means it's in a way, it's a way of calculating. It measures and puts a point in this like a virtual space, and if you're somehow static, your points are going to be all at the same place. If you've been moving, then you're here, and then you're here, and then you're here. So it calculates somehow a volume, and then this volume is can be after these patterns of volume can be attributed to certain activities. So it uses a hidden markup algorithm trained to recognize walking, jogging, sprint, running, stair climbing, etc. So this is showing the use of the home PC with the heart sensor and the activity sensor. I have a little video I can just show it to you. I explain. So this was used once a day by the subjects in this study. So the person is logging into the home PC. And first has been wearing a sensor, so first has to remove the sensor and download the data. So the person is then scanning to find the sensor. And then the sensor is going to be found, and she clicks to select it, and then she downloads the data. This is done wirelessly by RF, so the person has to stay near the computer. Now she's removing her heart sensor, and she's going to download the data. So these are the pads that were used here. She's removing the pads. This is the heart sensor. And now she scans to find the heart sensor, which is there. They all have a specific address, and now she downloads the data, which is going to be sent on the Optimus server later on. Now she's putting back the sensors. She's taking the sensors that are fully charged, and she's putting the sensors that she's been using on the charger, which is a contactless inductive charge. And now she's going to try to activate the sensors. So she's scanning to find the sensors. She finds activity sensor, so she's going to activate. So now it's starting to record, and it's going to do the same with the heart sensor. So this is actually showing how to wear the sensor with alcohol, the pads. They can be put here, 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 at different places. And then wearing as a necklace. And you can take a shower also with the sensor and the water. So she's selecting the sensor and she's activating the sensor. And so then 24 hours later, she's going to be doing this ritual of removing the sensor, downloading the data, and there comes the sleep diary and the questionnaires. So the use of the EEG for recording once a day was somewhat the same, except there was a recording of 80 seconds. The person puts on the sensor, goes for the signal quality, finds the signal. When the signal is good enough, then the user is able to make a recording with eyes closed, and then after downloading the data in the same way. Both ECG and EEG sensors support the biofeedback streaming of calculated results, which was done in the studies more as a choice of the user to train. So mainly you can train your heart rate variability or your brain waves, or your brain waves in a certain mode to enhance relaxation. So I'll show you the neurofeedback training. I don't have the time to show you everything, but you can get ideas of what it is.